Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to work through a few examples which go with the section on optics and wave effects. This is the chapter which corresponds to Chapter 7 in your Shipman, Wilson, Higgins, and Torres Physical Science textbook. As always, before working through the examples, it is worth looking at a few of the important equations that go with this chapter. So I've collected a few of them here, and of course your textbook will provide a few of them at the end of the chapter right before the exercises. So this is a combination of the ones that I've put together for you and that your textbook has for you. So let's look at a few of those examples now. For our first example, we have the question, what is the speed of light in water? To answer this question, it's useful to look up the index of refraction of water, and that can be done by looking at table 7.1 in the Shipman Physical Science text. So here are the indices of refraction of a few common materials. So for water, we see that the index of refraction is 1.33. If you look at the formulas which I showed, which were the relevant equations for the chapter, one of them says that the refractive index of a medium is the speed of light in vacuum divided by the speed of light in that medium. So that means that the refractive index times the speed of light in a given medium is also equal to the speed of light in a vacuum. And so that means that the speed of light in a medium is equal to the speed of light in a vacuum divided by the refractive index. So for water, what we would have is something like this. We'll use the approximation of 3.00 times 10 to the 8 meters per second divided by the refractive index for water, again, was 1.33. So we can put this into our calculator. 3 divided by 1.33 gives us 2.2556. And of course that 10 to the 8 is going to remain unchanged, so the speed of light in water is going to be approximately 2.26 times 10 to the 8 meters per second. Follow-up example to this, what is the speed of light in diamond? So again, we're going to want to look up what the refractive index is for diamond. So again, we look at table 7.1 in your text, and we look down where we see diamond, and we see that the refractive index for diamond is 2.42. So that's again table 7.1 within the Shipman textbook for physical science. So we have that the refractive index is the speed of light in vacuum divided by the speed of light in a medium. So this means that the speed of light in diamond times the refractive index for diamond is equal to the speed of light in vacuum, and therefore the speed of light in diamond is equal to the speed of light in vacuum divided by the refractive index of diamond. So this is approximately 3.00 times 10 to the 8th meters per second for the speed of light in vacuum divided by the refractive index of diamond, which again was 2.42. So let's plug those guys into our calculator. 3 divided by 2.42 gives us 1.239669. So, and of course that 10 to the 8th part remains unchanged, so the speed of light in a diamond is approximately 1.24 times 10 to the 8th meters per second. So it's a bit slower than the speed of light in water, and a bit slower, of course, than the speed of light in vacuum. So that's how you find the speed of light in any general medium. Pretty important point for our first pair of examples. Let's look now at another example, which is of similar type. Our next example asks, how long does light take to travel through a 1 kilometer long optical fiber whose core consists of crown glass? And we're going to assume that 1 kilometer is the actual length of the path taken by the light as it makes its various reflections. What I mean by this is light traveling through an optical fiber usually does something like this. So I'm drawing right now the optical fiber. The light itself is going to do something more along the lines of coming in through one end of the fiber, hitting a wall, bouncing off, hitting the next wall, bouncing off, hitting the next wall, bouncing off, hitting the next wall, bouncing off, and so on until it leaves the fiber. So we're assuming that the actual path length that this light takes with all these bounces, all this zigzags, if you add them up, is a kilometer, not that the fiber itself is a kilometer. So once again, we're going to want to look up what the refractive index is for the material that makes up this optical fiber, which recall was crown glass. So we return to table 7.1 in the Shipman Physical Science text, and we see that for crown glass the index of refraction is 1.52, so we're going to need that. So we have, our information is that for the refractive index we have 1.52, and for the total path length we have 1 kilometer, which is the same as 1,000 meters. And we wanted to know how much time it's going to take for the light to travel this distance. And as you recall from simple kinematics, the distance over the time is what is defined as the average speed of an object. So in this case, that average speed, we use the speed of light within this medium. So we're looking for speed of light in crown glass to do this. So I'm going to go ahead and solve out this equation for the delta t, and then we've got to find numbers to plug in for delta x, we're already given, and for this guy, which we don't have. So to solve for delta t, this thing becomes delta x is equal to speed of light times delta t. And so that means that the time that it takes times the speed of light is equal to delta x. I write this extra step because I know a lot of you get lost on that step sometimes. So that means that the time it takes should be delta x over c. So the time it takes to get from one end of the fiber to the other is the path length traveled by the light divided by the speed that the light is traveling at. So we need to know what speed is the light traveling at. Now, again, we have this equation that says that the refractive index is going to be equal to the speed of light in vacuum divided by the speed of light in a medium. Okay, so that means that the refractive index times the speed of light in the medium is equal to the speed of light in vacuum, and that in turn means that the speed of light in medium is equal to the speed of light in vacuum divided by the refractive index of the medium. So we now have stuff we can plug in because we have the refractive index of the medium, and the speed of light in vacuum is a universal constant. So 3.00 times 10 to the 8th meters per second divided by 1.52. So that means that the speed of light in the crown glass is going to be a little less than 2 times 10 to the 8th. So 3 divided by 1.52 gives us 1.97, and then of course times 10 to the 8. So we can write that this is 1.97 times 10 to the 8th meters per second. And now that can be plugged in over here for this equation. So our delta T, therefore, is going to be 1 kilometer or 1,000 meters, which is the same as perhaps writing 1.00 times 10 to the 3rd meters, and we're dividing that by 1.97 times 10 to the 8th meters per second. So let's go ahead and put in our values. So 1 divided by 1.97 gives us 0.508. So that is equivalent to saying 5.08 times, now we got to figure out what our power is going to be. So to make it 5.08, we've already reduced this from 10 to the 3rd to 10 squared. Now we're dividing that by 10 to the 8th, so we end up with 10 to the minus 6 seconds. So this is how much time it should take the light to travel from one end of the optical fiber to the other end. So again, it will take 5.08 times 10 to the minus 6. This is the same as saying 5.08 microseconds to travel through a 1 kilometer of crown glass. Our third example here is actually an example that kind of stretches across 2 chapters. Given that the frequency of light remains constant regardless of medium, what is the new wavelength of light which is 532 nanometers in vacuum as it passes through water? I know it's tough to do examples that cover more than one chapter, and that we've already done one such example in the previous example. It is kind of difficult to remember kinematics when you're working with optics, and it's kind of difficult to remember waves when you're doing optics problems. But just as a little refresher, let's look back at how wavelength and speed and frequency are related. So of course this is drawing from some information that was covered in the lectures on waves and sound, which corresponded to chapter 6 from your introductory physical science text. And if you review that chapter or that lecture, you will recall that the speed of a wave is given by the wavelength divided by the period of the wave, or more relevantly here, the speed of the wave is given by the wavelength times the frequency of the wave. So we have V is equal to lambda f, and since we're talking about light, that means that the speed of the light in a given medium should be equal to the wavelength of the light in that medium times the frequency of the light. Now, we've been told that the frequency does not change, so frequency is constant. So one approach to this problem would be to determine what the frequency of light at 532 nanometers in vacuum is. And you would do that basically by rearranging this equation up here. So you'd have C divided by lambda is equal to F, and that means that F is equal to C over lambda m. So in this case, the actual medium that we might want to use is vacuum, and so you'd have this is equal to C in vacuum over lambda in vacuum, which would be 3.00 times 10 to the 8th meters per second divided by 532 nanometers. So you'd have to convert this nanometers into meters. Recall that 1 nanometer is equal to 10 to the minus 9 meters. You would then need to figure out what the new speed in water is, and you could then do that by basically rearranging this equation up here. So you'd have lambda m times F is equal to Cm, and so lambda m should be Cm over F. Right, so you would have to figure out what the new speed is in water. So again, the index of refraction of a medium is always the speed of light in vacuum divided by the speed of light in that medium. This means that the speed of light in a medium times the refractive index in a medium is the speed of light in a vacuum, and so you'd have that the speed of light in a medium is equal to the speed of light in vacuum divided by the refractive index of the medium. So for water, you'd put 1.33 for this number right here. So this is 1.33, and again you get that off of table 7.1 from your text. So that is one way of doing it. Another way of doing it is to come back up here and notice this equation right here that we have. That frequency is the speed of light in a medium divided by the wavelength in a medium, and we have that frequency is invariant. That means that frequency in vacuum is equal to frequency in water, and so if the left-hand side of an equation is equal to the left-hand side of another equation, then the right-hand side of those two equations should also be equal. So that means that the speed of light in water divided by the wavelength in water should be equal to the speed of light in vacuum divided by the wavelength in vacuum. And I'm going to put a little 0 here to represent that it's the speed of light in vacuum. That's the maximum speed of light and therefore actually also the maximum wavelength. Okay, so the thing that we were looking for is what is the wavelength in water going to be? So we got to rewrite this equation a little bit. So we need to multiply both sides by that wavelength in water. So we have C naught over lambda naught times lambda water. Okay. Now for the hard part of this equation for a lot of you guys, we need to make sure that the wavelength in water is on the the left-hand side, because that's what we're trying to solve for. So the equation now looks like this. Okay, here comes another tricky thing. We got to get both of these terms over here onto the other side of the equation. So the way that we could do that is we have to multiply both sides by C naught, divide both sides by C naught, multiply by lambda naught. So now we have seawater times lambda naught divided by C naught. So now we're ready to start plugging some numbers in. And in case you've forgotten already what the speed of light in water is, we happen to have solved that in one of the earlier problems. It's the first example I did, so you can rewind if you'd like to figure out how to solve for the speed of light in water. 2.26 times 10 to the 8th meters per second, and that's being multiplied by the vacuum wavelength of 502 nanometers, and then we have to divide that by the vacuum speed of light, which is 3.00 times 10 to the 8 meters per second. So I notice that the 10 to the 8s both cancel, and I notice that the meters per second both cancel, so I'm going to be left with nanometers. So now we're going to have to do a little bit of multiplication and division. So we pull out the calculator, we multiply 2.26 by 532, and we divide that by 3, and we get 400.77 nanometers. So that means that the wavelength in water, which is what we solve for in all of this, is about 401 nanometers. So in other words, if we're using a neodymium YAG laser that's frequency doubled, then the wavelength which of that laser happens to be 532 nanometers, the wavelength in water is going to be 400 nanometers. We have light which is incident on water from air at an angle of incidence 60 degrees. We want to know what's the angle of the refracted beam. Alright, quick quiz before I answer that. You see here a picture with red, green, and blue light, both in air, and then here's water, and here's in air again. And the question is, which of these beams is the initial beam, the first incident beam, and what beam is being refracted and what beam is being reflected? Can you figure that out by looking at this picture? Maybe one hint is the fact that you don't see a blue beam over here, so presumably this is not the direction from which everything is incident. Even without knowing how light works, you should be able to figure that part out. The red beam, green beam, blue beam, though, are actually incident from over here. And this right here is a reflected red beam and a reflected green beam from the surface of the water. This right here is the refracted red, green, and blue beams. So you can see that they have bent a little bit from their original path. That is refraction in action. So to solve for this, we should use what's called Snell's law, which gives us a relationship between refractive index and angle of incident versus refractive index and angle of refraction. So this in the equation is the refractive index of the media that we're incident from. So this is the medium that you start off in. This one is describing the medium that you're going into. So the refractive index of, let's say, air times the sine of the angle of incidence is going to be equal to the refractive index of glass, or in our example actually water, times the sine of the angle of refraction. And notice the other thing is that both of these angles are taken from the perpendicular. So angle 1, that 60 degree angle, is 60 degrees from this dashed line. That light's coming in like this, and then it is refracting into the water or glass, and so the angle we're finding is an angle from the normal inside of the glass, or in our example, inside of the water. So here's a simple diagram that's sort of showing how that works out from the side. We're incident from air at some angle theta 1 into water at some angle theta 2, and we were given that theta 1 is equal to 60 degrees, and so we're trying to find what is theta 2 equal to. And to do that, we're going to need to know the refractive indices of air and water, and I have actually put those into the drawing for you. But if you didn't know them, then you'd need to go look them up somewhere, like say table 7.1 in your textbook. So Snell's law tells us that the first refractive index, N1, times the sine of that first angle, theta 1, should be the second refractive index times the sine of that second angle. So what we're looking for is this term right here. So we need to solve for that. That means that we need to rewrite our equation. I'm going to do that by subtracting N2 sine theta 2 from both sides of the equation. Okay, and now I'm going to multiply everything by -1. So N2 sine theta 2 minus N1 sine theta 1 is equal to 0. Now I'm going to add an N1 sine theta 1 to both sides of the equation. So N2 sine theta 2. So we're adding a plus N1 sine theta 1 here, and that means we need to add a N1 sine theta 1 here. So N2 sine theta 2 is equal to N1 sine theta 1. So that's your first few steps. I know that this may be a lot to follow for some of you, but bear with me here. We're trying to solve now for this theta 2, so we should probably divide both sides by N2. So you're left with sine of theta 2 is equal to N1 over N2 sine of theta 1. Now, the way that you get the angle theta 2, if you're given the sine of the angle, is you take what's called an arc sine or an inverse sine. That means that theta 2 is going to be inverse sine of N1 over N2 sine theta 1. Okay, the good news is that that sine inverse button is a button on your calculator that you push. So what we have here basically is inverse sine of 1.00 over 1.33 times the sine of 60 degrees. So let's put that into our calculator and see what we get. The order of operations that we need to use is that we should basically multiply this guy by the sine of this guy, divide by this, and then after doing all that, take the inverse sine. So the inverse sine, by the way, there's an inverse button. You click inverse and then you click sine on my calculator. So we go 1 times, in order to get the sine of 60, I have to enter the 60 first and then push sine. So you can see up here I've got 1 times sine of 60. This d is just telling me that I'm in degrees. Okay, and now I have to divide that number by 1.33. Okay, now I've got this whole number that's in here. So this whole number in here is 0.65114 or whatever. So all of this right here comes out to about 0.65 whatever. So Now we click the inverse button, and look, there's a sine -1 button now, so we click that, and it tells us that the angle should be 40.628 degrees. So we just solved for theta 2, and theta 2 was 40.628 degrees, and we're actually going to want to keep about 3 significant figures worth of that, so 40.6 degrees. Next example, you have light incident on a crown glass cube. That means a cube made out of crown glass, kind of like this little cube, which may or may not be actually made out of crown glass. And the light is incident at an angle of 30 degrees. And the question is, what will be the angle with which it exits the opposite face of the cube? So it's basically coming in on this side at 30 degrees. So maybe like this. It refracts. It hits this other side and it refracts again and exits. And we want to know, what is this exit angle going to be? Yeah, this question is a lot harder than the last one, because now you have to figure out both, in order to get this angle, which is what we're ultimately looking for, starting from this angle, you've got to figure out what this angle is, then you got to figure out what this angle is. So you got to apply Snell's law once here, then you got to actually know some geometry, and then you got to apply Snell's law here. So there's really 3 steps involved to this problem. The good news is that the second step is actually really easy, because it turns out that this angle and this angle have to be equal. So this right here is also equal to theta 2. So once we find this angle, we've got this angle, and so it's actually a 2-step problem. All right, well, let's do Snell's law. So we have N1 sine theta 1 is equal to N2 sine theta 2. All right, we're solving for theta 2. This is going to be the same process as we used in the previous one. So basically all the same steps that we just took. So what was the final equation that we had there? It was theta 2 is equal to sine inverse of N1 over N2 sine theta 1. Okay, so now we need to plug some numbers in. If you don't know where this equation came from, you should probably rewind to the last example. So theta 2 is therefore going to be equal to sine inverse of 1.00 divided by 1.52 times the sine of, remember that theta 1 was given, and theta 1 was given as 30 degrees. So we have a sine of 30 degrees in here. Okay, I guess we need our calculator then. So 1 times the sine of 30 divided by 1.52 gives us 0.3289. So now we have to take the inverse sine of that, and what we get is 19.2 degrees. So theta 2 is equal approximately to 19.2 degrees. All right, now we got to do Snell's law again. So Snell's law, so this one's also 19.2 degrees. Now we're doing Snell's law to get back out. So we now have to use N2 sine theta 2 is equal to N3 sine theta 3. Okay, well, since this equation is a new equation, I guess we'll have to go through all the steps to figure out what theta 3 is. So you know, subtract this from both sides, multiply by -1, then add this to both sides, and if you do those 3 steps, you end up with n3 sine of theta 3 is equal to n2 sine of theta 2. Okay, so now we need to divide both sides by an n3 in order to isolate the sine of theta 3 term. So now I have a sine of theta 3 is equal to n2 over n3 sine of theta 2. Okay, so I'm trying to solve for theta 3. So I hope everybody remembers how to get theta 3 if you're given sine of theta 3. If you don't remember, then you take an inverse sine of both sides. So theta 3 should be inverse sine of n2 over n3 sine of theta 2. Now we can plug some numbers in. So theta 3 should be the sine inverse of, so n2 is the refractive index of the glass, so that's 1.52, and n3 is the refractive index of the air, so that's 1.00. And then we have sine of theta 2. Well, theta 2 was found back over here, was 19.2 degrees. Okay, so let's go ahead and use our calculator now to figure this one out. So, well, this was the answer for that theta 2, so we can just take the sine of that. And then we should multiply by 1.52. And now we should divide by 1. I hope you don't actually have to use your calculator to do that operation, but in case you do, that's how you do it. So now we have to take the inverse sine of it. What do you think we're going to get? 30. So I guess that means that theta 3 is 30 degrees. And that means that for a cube, if you come at some angle of incidence on one face of the cube and you exit from the parallel face of the cube, then your initial incident angle should also equal your final exit angle. So that's kind of a interesting result. If you're using anything that has 2 parallel faces and you enter through one parallel face and you exit for the other, and you don't have lots of bounces from internal reflection, then this incident angle and this exit angle should actually be equal. Even if you do have bounces from internal reflection, so long as the faces that you're bouncing off of are all parallel, you will get pretty much the same result. Just maybe that you're exiting out, coming out this way, for example. So let's look at our 6th example, which is a critical angle example. In other words, we're doing total internal reflection. You can see a picture here of total internal reflection. Here they're shining a laser into a glass of some water, and you actually can kind of see, if you were to draw a line where this laser is, that it is refracting here. It's hitting the surface, and then you don't see any light coming out, you just see the whole thing bouncing off the surface, and then actually you can figure out the refraction again to get to here. So this is total internal reflection. By the way, for those of you who are going to try this kind of thing at home, if you want to see the laser in water show up pretty well, there's a little pro tip. You can add a couple drops of milk to the water and it will make the laser show up a lot better than if you just use plain water. So that's why A, the water is murky here, and B, why you're able to actually see this laser. So let's figure out what that critical angle is for light to totally reflect from this interface, shall we? To do that, you should maybe review briefly your notes, and in particular, Snell's law is useful to us here. Snell's law is telling us that n1 sine theta 1 equals n2 sine theta 2. You get that critical angle because at some point you find that you can no longer take the sine of the angle and get an actual, you can no longer take the inverse sine of the angle and get an actual number anymore. So, for example, if you were going to isolate theta 2 or theta 1, maybe you're solving for theta 1, you have sine of theta 1 is n2 over n1 sine theta 2. For some value of theta 2, this whole product becomes greater than 1, and you can't have the sine of some real angle and take that sine and end up with greater than 1. At 90 degrees, you get the biggest value for sine, and that's equal to 1. Okay, so what I'm saying here basically is if you were to solve for theta 2, and as a result of solving for theta 2, you got sine inverse of refractive index 1 over refractive index 2 sine of theta 1. Alright, well, so long as this whole product that's inside these parentheses is less than 1 or equal to 1, then this operation will work. But if it is greater than 1, then you will get an error message from your calculator. This is basically not okay. And I'll just demo that for you just for fun. Let's put in a random number, let's say 2, and we hit inverse and we put sine inverse. Oh, invalid input. So 2 is bigger than 1, you get an invalid input. Maybe we'll make it, now the calculator doesn't even want to operate because of that. Let's go ahead and put in like a 1.00000, lots of zeros and a 1. Let's try the inverse sine of that. What do you think we're going to get? Oh, invalid input. So still not okay. Okay, gotta restart the calculator each time that it does that. Alright, what if we put in 1 and we take the inverse sine of that? Oh, we got a number back, 90 degrees. So what we're basically doing here is we're solving for theta 2, in which theta 2 is equal to this inverse sine of this ratio, in which we put the sine here being 90 degrees. So this angle right here becomes 90 degrees. And the reason why this angle needs to be 90 degrees is because that means that you get the biggest possible number for this product right here. And we're assuming here that theta 2 is, you're going from your high to your low refractive index. So N2 will be bigger than N1. And so that's going to give us the biggest possible angle that you'll get refraction out of. And in fact, it will refract out at 90 degrees, which basically would look something like, if I can draw, your light comes up, hits here, and your refracted light basically just skims along the surface. So anything, any greater angle, such as this, then you're going to get no refraction and the entire beam will reflect. Alright, so that critical angle in this case is going to be, again, we're doing this for water, so it's going to be sine inverse of 1.00 divided by 1.33 times the sine of 90 degrees. So let's pull up our calculator again because we need to do this calculation. So 1 times, we need to do the sine of 90 degrees, it's 1, and now that's got to be divided by 1.33. So we get this number here, that's what's going inside of this inverse sine, so now we got to do an inverse sine. and the answer is 48.76. Excuse me, 48.75 degrees. So that means that if you're going from water into vacuum, then the maximum possible angle that you can take and still get a refraction is about 48.8 degrees. By the way, if you go the other way from vacuum into water, you'll find that you always get some refraction, so long as there's not anything silly going on like polarization effects, that kind of thing. So that means 48.8 degrees if you were to draw a dotted line and measure the angle from this beam to that dotted perpendicular line. It's got to be less than 48.8 degrees if you want to see a beam come out here, and if it's greater than that angle, then you'll get this effect here. And since air has a very similar refractive index to vacuum, you're going to find that it's also about 48.8 degrees for total internal reflection from water into air. So what we want to know is, what's the focal length of a concave mirror whose radius of curvature is 2.0? Okay, this basically means that you've taken a sphere which has a radius of 2.0 meters, and from that sphere you have sliced off a little edge, and that edge is what your mirror is going to be made out of. And if you were to go back and review those important equations for the chapter, you would find that there's a relationship between radius of curvature for a spherical mirror and focal length for the spherical mirror. Specifically, the focal length is midway between the center of this sphere from which the mirror was chopped and the point at which this principal axis meets the edge of the mirror. So that's another way of saying that the focal length is half of the radius. So the focal length is the radius of curvature divided by 2. That means that it should be 2.0 meters divided by 2. And so what should that be? Well, you guys may need to use your calculators to solve this one. So let's see here, 2.0 divided by 2 gives you what? It's a 1 meter focal length for this mirror. So the focal length of the mirror should be 1.0 meters. And that's for this spherical mirror whose radius of curvature was 2 meters. Alright, so let's look at another example with a mirror then. This example, we take an object of height 1 meter and we place it in 2 meters from a convex mirror whose radius of curvature is 3 meters. And we want to know what's the image going to look like, and then let's try to repeat it for a concave mirror. So in order to solve this problem, one thing that you could do is draw a ray diagram, and the process for doing that is described in the end of section 7.3 of your Shipman physical science text. Basically what you do is you draw your object away from your mirror. You draw one ray which is parallel to the principal axis, and what that ray is going to do is it's going to reflect through the focal point. Then you draw your next ray so that it goes through the center, and so what that ray is going to do is it's going to hit and then it's going to reflect directly back along the direction that it came in, and wherever these two rays cross, that's where the image is formed. And it could be in some cases that the two rays don't cross over here on this side of the mirror, and in that case you can extend the reflected rays, so this ray would sort of extend off this way, this ray would extend off this way, and if it, in some geometries it turns out that these little extended rays cross, and in that case you'll get actually a basically a virtual image. In this case you get a real image. So that's the process for solving it. You can also use the equation which I gave you in your notes. That equation is the one that's on that image characteristics slide. Your book doesn't really give you this equation, but it may be an easier way of doing things than drawing an image more or less to scale and drawing a ray diagram. Basically, this is saying that 1 divided by the object distance, so distance between object and mirror, plus 1 divided by the image distance, distance between image and mirror, should be 1 over the focal length. So you would solve this for the image distance. Then you can get the magnification by using negative di over do, distance of image over distance of object, bearing in mind that if the image forms a real image, you're going to have a positive number for this. If it's a negative, then this one will be a negative number. And so a real image in this case is going to be a positive magnification and therefore upright, and a negative number overall means a virtual image and therefore inverted. In any case, if you wanted to draw the ray diagrams, this is roughly what the ray diagram is going to look like if you had a convex mirror. So a convex mirror, this is the mirrored surface. I actually draw a third ray, and this third ray is such that a continuation of the ray would basically just pass through the center point on the other side of the lens, and so that's equivalent to that second ray in yours. The extra ray on mine has a starting point at the top of the object and hits right at the principal axis with the mirror, and what that one does is it reflects away from the mirror at the same angle from the principal axis as the incident had. So that's a third line that gives us a double check. With the first two, you'll notice that all three cross in the same place, and so this is how tall the image is. So you can see in this case that the image is actually virtual, and it is upright, meaning the arrow is still pointing up. Arrows up here, arrows up here, and it's actually smaller than the object. Then for the concave version, I did the same 3 as I drew for this one. So here's the original object. Here is the ray that's parallel to the principal axis. It reflects through the focal point. Here is the ray that is directly to the point where the mirror meets the principal axis, so it reflects away such that this angle and this angle are equal. And then I drew one ray right here, which would be through the center, and so it's retroreflected, and you'll notice that all 3 end up crossing through the same point here. So in this case, the image is upside down, and it is real, and it is larger. So upside down means inverted. It is a real image because it's appearing on this side of the mirror, so the 3 rays really do cross through this point, and it is actually larger than the original object. So the original object is this long, the image is this long. Basically, if you can stick a card over here, if I put a card over here and an image forms on that card, then it's a real image. Whereas over here, if I actually put a card back here somewhere, there would be no image formed on the card. Even though you see the image, if you're standing here, you can see this image, you don't actually have any real light rays crossing through that point where that image is formed. If you drew it to scale, you could actually measure all of these distances out, and you'd be able to get the actual location from the mirror. You could also again use that equation to do this. Alright, let's try another one. Let's do something specific in which we have an object which has an actual height 0.18 meters, and we place it some distance from a convex mirror with a specific focal length. So let's figure out what is the image going to be like. How tall is it? Where is it? Is it virtual? Is it upright? Etc. I kind of fooled with you a little bit there by putting an image of a mirror because the problem actually is calling for a lens. But you can still draw a ray diagram, and if you've drawn it to scale, you'll get the right answer. Again, there is instructions for how to draw a ray diagram for a lens in your text in section 7.4. In fact, figure 7.26 shows you the steps involved. I actually have drawn here 3 rays. The first ray is initially parallel to the principal axis. It goes through the focal point on the other side as a result. The second one goes straight through the principal axis at the point where the principal axis meets the lens. So that means that it is undeflected ultimately by refraction. So I can just draw a single straight line for that. The third one is sort of a double check line if you want it. I drew so that it goes through the focal point on this side of the lens, and that means that on the other side it should be parallel to the principal axis. So where those 3 points meet is where the head of the image should be. So they generated from the head of the object, they're going to end up at the head of the image. So you can, if you've drawn everything to scale, this thing is 1.2 meters. This thing right here is 0.8 meters or 0.8 meters for this as well. That means that you should be able to measure this length and you will come up with 2.4 meters. You can also do this by using the equation, however. And the equation looks very much similar to the equation that we just used for the mirror. In fact, the terms all are the same and have the same meaning, although there might be a little difference in sign convention. So let's do the equation, and if everything goes right, then the image distance that we'll get at the end is still going to be 2.40 meters as a double check. The equation looks like this: 1 over the object distance plus 1 over the image distance is 1 over the focal length. All right, well, we're solving for this term initially. So that means that 1 over the image distance is equal to 1 over the focal length minus 1 over the object distance. Now, you could try to solve this equation by basically getting a common denominator and multiplying this term by dO over dO, this term by F over F, and what you would basically get is dO minus F over F times dO, and then you could take a reciprocal if you so desired at that point. However, that's not necessary to solve the problem in this case. So basically what I'm saying here is that the image distance you can get by reciprocaling this thing, F times dO over dO minus F. But that's not strictly necessary in as much as we can solve for 1 over di, get a number, and then take the reciprocal of that number. So 1 over di is going to be equal to 1 over 0.80 meters minus 1 over 1.20 meters. We can plug those things into our calculator, and what we're going to get is 1 over 0.8 gives us 1.25, so might as well just write that out. So this is 1.25 inverse meters, and then from that we're subtracting our 1 divided by 1.2. So we're subtracting 0.833 inverse meters. Okay, so what is this going to give us? 0.41666, etc. So we'll just call that 0.417. inverse meters. Okay, well that's equal to 1 over di. So if I want to get di, I need to multiply, I basically need to take reciprocals, which is the same thing as saying 1 over this thing is equal to di. So whip out that calculator again, still has that number on it, and we just hit the 1 over x button and it gives us 2.4. So sure enough, we ended up getting 2.4 meters. Our next step actually is that now we need to know what kind of an image is it going to be. So we use this magnification equation that says it should be negative di over do, and so that's negative of 2.4 meters divided by 1.20 meters, because 2.4 was our di, 1.2 was our do. So some of you may need to use a calculator to do that. Others maybe see that it's actually pretty straightforward, should be 2. So this gives us negative 2.00. So our magnification is negative 2.0. The fact that it is negative means that it is going to be inverted. Okay, and sure enough, it's inverted. The fact that the magnitude is greater than 1 means that it should be larger than the object. It's hard to see on this diagram, but you can probably see that it is in fact larger here than here. In fact, it should be twice as tall as the original object. So since the original object had a height of 0.18 meters, that implies that the image should have 0.18 times 2. So the height of the image is actually going to be negative 0.36 meters. Again, that negative number for the height just means that it's going to be upside down, inverted. And we found that it's located 2.4 meters after the lens, and since it's on the back side of the lens, since rays really do converge there, this is a real image. Alright, let's look at one more example. You have an object of height 0.18 meters and it's placed 1.2 meters in front of a concave lens of focal length 0.80 meters. So now what's the image going to look like? And once again, I've kind of lied to you in my pictures. This is a mirror, not a lens. But that's okay because a lot of the principles will still work out the same. Again, you can review how to draw a ray diagram. For example, figure 7.26 shows it. 7.26 looks like this, but without all this information about convex lenses. Basically, this right here is showing us the convex lens diagram. You want to draw a single ray that is parallel to the principal axis, and that in principle is going to have some ray that reflects through the focal length one way or the other. Then you will also want to draw one that goes straight through the principal axis where the lens meets that principal axis, and that one would have basically a straight line approach, no deflection. So these two actually do not intersect on the back side of this lens. Instead, you have to extend these dotted lines to find where the image is. Again, this is for a convex lens, but the steps are going to be similar. So here you see the ray diagram that I've drawn for the concave lens. Basically, you draw one ray which is parallel to the principal axis, that ray is going to deflect off this way, refract off this way through the lens. Draw a dotted line back along it and it will go through the focal point. In the other direction, you draw a single straight ray which goes right through this point where the principal axis is in the middle of the lens. If you drew a dotted line back away from it, it would just basically continue to trace out the same path of the original ray line in the other direction. So we look for where these two lines cross, and that's where the image should be formed. You can see in this particular image that the image is located 0.48 meters from the lens. You can see that it's smaller than the original object. If you measured the height, you'd get actually 0.072 meters. And you can see that it's upright and that it is in fact virtual because we're using these dotted lines to create that image. You can also use the equation, which is going to show that 1 over dO plus 1 over di is equal to 1 over f. In other words, 1 divided by the object distance from the lens plus 1 over the image distance from the lens should be 1 over the focal length of the lens. So that means that 1 over di should be 1 over f minus 1 over dO. And now we can plug some numbers in over here. So that's 1 over, okay, recall that the focal length is 0.80 meters. But since it's a concave lens, this is actually a negative. Okay, and that's going to be minus 1 over, and this was 1.20 meters. So we should plug those guys into our calculator. And again, what we're going to get is this. So let's say 0.8, it's got to be negative. We need to know what 1 over that is. So minus 1.25 inverse meters minus an additional plug in the 1 over 1.2, and what you get is 0.833. So minus 0.833 inverse meters. So all of this together is going to give us a total of negative 2.08 meters. 2.08 inverse meters. So now we take a reciprocal to get di, and what that's going to give us is minus 0.48. So the image is formed minus 0.48 meters, that's 48 centimeters, from the front of the lens. So this is 48 centimeters and it's on the same side of the lens as the object. Now we do the magnification. Again, it's negative di over dO. So that means it's going to be negative of minus 0.48 meters divided by the 1.20 meter for the object. So let's see what that gives us. So divide by 1.2 and then get a negative of that is 0.4. So the magnification is 0.40. It's positive, so that means that this is going to be upright, and this fact means that it's going to be smaller. And in fact, the height of the image is always given by the magnification times the height of the object. So our image height should be 0.40 times 0.18 meters. So plug all that stuff into your calculator, and what do you get? You get excuse me, it should be 0.4 times 0.18, plug the wrong number in, 0.072 meters. So our image height should be 0.072 meters. All right. So in this case, the image is going to be a virtual upright image with a height of 0.072 meters, located 48 centimeters in front of the lens. So again, this is actually showing for a concave mirror. We wanted a concave lens, but you will in fact get a virtual image just as in this picture. It's just that the virtual image is maybe formed over here somewhere, and it's going to be smaller than the object rather than larger. So that's all of the examples for this chapter. I hope that you found this video helpful, and thanks for watching.